Optimal Sub-Gaussian mean estimation in very high dimensions. I'm Paul Valiant, and this is joint work with Jasper. Today I'm going to tell you about two problems which at first glance don't seem particularly related. The first problem, which gives this talk its name, is mean estimation. This is the classical challenge from statistics that, given samples from, today, a high-dimensional distribution, we want to estimate the distribution's mean as accurately as possible given our data. More on this in a moment. The second challenge, which has a rather different flavor, is that of coming up with good tail bounds in high dimensions. The setting is we have a sum of independent bounded random vectors of some total covariance, and we want to come up with a high probability bound on the distance from their mean. The guiding idea today is that a high dimensional Gaussian distribution looks like a spherical shell. To illustrate this, consider the distribution of the length of standard Gaussian distributed random variable in d dimensions, normalized by 1 over root d. In one dimension, this doesn't look very much like a spherical shell. But as you increase the dimension, you can see that the radius starts adhering more and more tightly to 1. The issue is that previous tail bounds don't seem to reflect this behavior. One way of saying this is that previous tail bounds seem to have an essentially uniform shape for all dimensions d, and fail to reflect the ground truth behavior that these distributions are converging in increasing dimension to a spherical shell. So these are the two challenges that I'll tell you about today. Let me more fully introduce the mean estimation problem now. The challenge is, given some data, how do we best estimate the mean of the underlying distribution? Mean estimation shows up as a subroutine in a variety of computational settings, but it's also one of the most important statistical primitives for dealing with real-world data. To use this as an example, supposing you're running a big experiment and you're collecting data from the real world. How can you best estimate the mean? I'm illustrating this in one dimension to emphasize that this problem remains hard even in one dimension. So given this data, how would you estimate the mean? Well, one good place to start is the sample mean. The sample mean works great for Gaussians and many other nice distributions. However, suppose we keep collecting data and we get a sample that's really, really far to the right. Is this an outlier? Should we take it seriously? Did we get unlucky? If there's only one of them, maybe you throw it out. What if you get two of them? So, okay, we saw two outliers out of the 10 data points we collected. What does this mean? Well, this data that we collected is consistent with a world where the expected number of outliers we see is, say, as low as 1/10, maybe as high as 4/10. And I'll use this to introduce the viewpoint that you should have about this problem. So in some sense, given the data, we're trying to figure out what are the most extreme distributions that could have plausibly led to the data we observed. And then given these plausible distributions, find an estimate that is accurate enough with respect to all such distributions. So meanwhile, there's some distributions that could less plausibly have led to our data. So if this event far to the right actually has a true probability of 1 out of 10,000, then it's pretty unlikely for us to see it twice in 10 data points. But I mean, pretty unlikely, well, only about 1 in a million unlikely. And how you should deal with this data crucially needs to depend on the confidence with which you want to return your answer. In some areas like physics, there's standards for publication that demand that you need to be more than 1 in a million confident in order to publish a paper. So if we were publishing a physics paper, we would need to account for the case that our data is generated from a distribution like this one. So the simple point here is that the optimal algorithm must depend on our desired confidence. So our goal is, given n samples from an unknown distribution p, we want to estimate the mean of p to within L2 distance epsilon, except with probability of failure delta. In other words, we want to understand the optimal trade-off between the number of samples n, the accuracy epsilon, and the desired confidence level delta. We're focusing today on the high dimensional case, where we define dimensionality in terms of what's called the effective dimension. If you haven't seen this before, this is the ratio of the trace of the covariance divided by the maximal variance in any direction. This is a very natural notion and behaves as you would expect. For example, for a sphere, the effective dimension just equals the ambient dimension. For a sphere, the variance is the same in every direction, and the trace just adds up one copy of this per dimension, thus this ratio just equals the dimension. Some distributions may have covariance matrix that looks more like a pancake, where there's several directions of big variance and several directions of small variance. Here too, the effective dimension does just what you would like. It essentially counts the number of dimensions with big variance and ignores the dimensions with small variance. So armed with this notion of effective dimension, I can now tell you what we mean by the high dimensional regime. Today, we're going to look at the case where the effective dimension is essentially bigger than the square of the logarithm of the desired confidence. So one way to get started here is by asking, how well can we do on a Gaussian distribution? And this can serve as a benchmark in general. So for Gaussian distribution, the best thing to do is just return the sample mean. And it's worthwhile figuring out exactly how well this performs. So given n samples from a Gaussian of covariance sigma, what does the sample mean do? Well, as we saw earlier, samples from a Gaussian in high enough dimension adhere to a spherical shell. So except with tiny probability, the answer will be extremely close to the square root of the trace over n, provided the dimension is high enough. So this is the case for Gaussian. And the algorithmic question is, to what degree can we get an algorithm that, not just on a Gaussian, but on any unknown distribution of unknown covariance, we want to approach this performance of a Gaussian? So what can we actually accomplish algorithmically? The punchline is that we can actually attain this, even down to the 1 plus little o of 1 factor, provided the effective dimension is high enough and for large enough n. There's been a lot of prior work in this area, including a lot of recent work in this area, even in one dimension. This area was in some sense kicked off by the classic median of means algorithm. More recently, a line of work culminating in our upcoming Fox publication has essentially resolved this question in 1D. The high dimensional case, though, looks much more complicated. It was only remarkably recently that the first algorithms with even constant factor sample optimality showed up, and at the cost of a huge computation time, which has been improved since then after a lot of work. This problem has also been approached from the rather different robust statistics perspective, where instead of a median of mean style algorithm, it uses an iterative filtering approach. So in some sense, this slide should convince you that this problem is hard from two perspectives. From a computational complexity perspective, the amount of work it's taken to improve the computation time shows that there's a lot going on here. And from a statistics perspective, the fact that it took so long to get even any algorithm is kind of scary. And also, even though these are constant factor optimal, the constants embedded in these are often huge. So one paper I looked at recently has a constant of 480,000 squared. By contrast today, the story is remarkably clean. I'm going to tell you a linear time algorithm that is sample optimal to within 1 plus little o of 1 factor. And I think you'll believe me when I show it to you. The algorithm is extremely simple, but at the cost of that the algorithm only works in very high dimensions. So our motivation for this work is that we want to do mean estimation. Gaussians are a natural first case to look at. And in some sense, the most interesting thing about high dimensional Gaussians is that they behave like spherical shells. So to take a closer look at this, the distribution of the error of a Gaussian distribution, except with probability delta, is described by the following expression, where the first term is exactly the square root trace thing describing the radius of the spherical shell. And the second term goes to 0 with increasing dimensions. So this becomes more clear if we rearrange slightly, and you can check my arithmetic with the definition of effective dimension. So the error becomes the square root of trace times 1 plus the second term, where if the effective dimension is a lot bigger than log of our confidence, namely this assumption, then the second term vanishes and the tail of the Gaussian converges to essentially just the spherical shell of radius square root trace. So given this Gaussian behavior, we're motivated to ask, can we extend these tail bounds beyond Gaussians? A good place to start here is to understand the one-dimensional Bernstein bound, describing how tail bounds on sums of independent random variables in one dimension that are each bounded by some radius r. Intuitively, the Bernstein bound combines two types of information. It combines information about the variance of each variable, but also a global bound R on the support of each random variable. As you can see, the denominator here blends these two types of information together. The first term that we call the Gaussian term is in terms of just the variance. And if the first term dominates the denominator, then you can see this ratio is just the standard tail for a Gaussian. However, as the radius bound gets bigger, these two terms start interacting, and the interaction shows how the Gaussian bounds gracefully degrade in the presence of outliers at radius up to R. So this is a one-dimensional Bernstein bound, and in this paper, we generalize this to high dimensions. The generalization is fairly natural. So given independent random vectors now in high dimensions, each bounded by some radius R, we aim to describe how closely the tail will adhere to the spherical shell of radius square root of trace. So for any gap t that's not too much bigger than this radius, we'll come up with a bound on the probability that the radius is t more than the spherical shell. And indeed, this expression is very similar to the one-dimensional expression where there's a Gaussian term coming from the maximal directional variance and a second term coming from the radius. It'll be a little bit easier to re-express this theorem using a different parameter gamma instead of t, which will make it look a bit less like the Bernstein bound, but it will be easier for us to use. So under this reparameterization, we're now asking what's the probability that the radius is 1 plus gamma times the radius of the spherical shell. So here the denominator has two terms, and if the first term dominates, then this expression essentially reduces to the exponential of half gamma squared times the effective dimension, namely the probability of being gamma close to the spherical shell decays exponentially with the dimension, thus showing that for any bounded distribution, the tails will adhere extremely close to the spherical shell and closer with increasing dimensions. So given this new tool of this high dimensional tail bound, how can we use it to do effective mean estimation in high dimensions? Well, one of the issues immediately is that the Bernstein bound applies to bounded distributions, but we want to do mean estimation in general. So how do we make our distribution bounded so that we can apply the Bernstein bound? Well, one simple idea is just to collect some data, throw out all samples that are outside of some ball of radius r, and then the samples conditioned on being inside the ball of radius r will come from a conditional distribution that's bounded, and we can apply the theorem. And thus, inside the ball, we get the desired spherical shell behavior. So the first step of throwing out all samples outside some ball, this gets better as the radius of the ball gets bigger. We're doing less damage to the distribution if we throw things outside, if we throw things that are outside of a big ball. The second step, though, performs better if the radius is smaller. This theorem has better performance for smaller r. So it takes some analysis to make sure that there's actually an r that satisfies both regimes. But still, algorithmically, given some data, how do we start? How do we pick a ball of radius r? Well, here's our algorithm. I think you'll agree it's really simple. So step one is that we find the center of the ball by roughly estimating the mean with just classic median of means algorithm on each coordinate. Step two, we pick some number s and throw out the s farthest samples from our center, returning the mean of what remains. And this is the algorithm. So I just want to say a few high-level things about the algorithm. First of all, it's linear time. Essentially, the most complicated thing we need to do here is just compute medians. Second thing, it turns out that the number of samples we throw out s can be almost any upper bound on the square of the log of our confidence. So this has this sort of remarkable implication that we can get an algorithm that simultaneously works for many different confidence levels delta. This is called in the literature a multiple delta estimator, and it's impossible in one dimension. Finally, just as a high-level comment, this algorithm throws out log squared of our confidence number of samples, which contrasts with the optimal one-dimensional algorithm from our Fox paper. in one dimension, you have to throw out log number of samples, whereas here we're throwing out log squared number of samples. And this gives some high-level sense of perhaps why our approach here can't extend transparently to the low-dimensional case. Our algorithm's error is 1 plus log of 1 factor optimal, and it's intriguing that we get such a tight algorithm from a perhaps not so tight tail bound. I'll illustrate this with a diagram. So consider the probability distribution of mean estimation error. So as we've discussed, the ground truth will adhere extremely tightly to a spherical shell. What if, however, we have a tail bound that adheres to the spherical shell, but maybe not so tightly? Are we okay? Well, even though the red and the blue curves differ a lot in the y direction, what we care about is the delta probability tails. And the delta probability tail of the error, even though these two curves differ a lot in the y direction, is very similar in the radial direction. In fact, the ratio, because both of these are so close to the spherical shell, is going to be 1 plus log of 1. This is why at a high level, getting this spherical shell tail bound is a big win. Given this tail bound, our algorithm is really simple, and it works for simple, robust reasons. The fact that this tail bound has such a simple and robust application here gives us hope that perhaps this tail bound will be useful in general. So because this bound is the main tool of the paper, it's worth saying a few words about its proof. The issue is that we're trying to understand a tail bound on the radius of a random vector in high-dimensional space. Well, one very simple way to get started is by taking one-dimensional Chernoff bounds in every direction x. So to draw a picture, we're trying to prove some bound on the probability of a vector being outside of a sphere. And for any direction x, we can just draw a yellow line perpendicular to x and compute bound the probability of being on the far side of this yellow line. We can do this for every x. It's not hard to check that if every point outside the sphere is hit by at least a c fraction of these Chernoff bounds, then this yields a bound of the probability of being outside the sphere of 1 over c times the average Chernoff bound. Because c appears in the denominator here, this suggests that in fact it might be to our advantage to move this yellow line towards the origin so that each of these Chernoff regions covers a bigger fraction of the sphere. We'll parameterize this by a distance beta, which we'll choose later. A second issue is that probability distributions in high dimensions can be very spiky in the sense that maybe they're supported only on the axes. And if the Chernoff direction x is aligned with a spike, then the bounds that we get might blow up badly. So one very simple way of trying to address this is that any support point y whose projection to the direction x exceeds some threshold p, we just set aside and deal with differently. So given beta and p, these parameterize our analysis and simply optimize over beta and p to get the best bound. So while this may seem a bit unprincipled, it uses simple techniques, the reason why we get such a tight bound is essentially the same reason that Chernoff bounds are so tight. The exponential in the moment generating function means typically very narrow regions contribute most of the bound, and therefore it's enough to find a beta and p that perform well on a narrow region. So even though these techniques are fairly direct and look fairly ad hoc, their good performance is essentially the same reason that Chernoff bounds get good performance. And this optimization technique is a simple and natural approach that yields the surprisingly tight and new bounds that drive our paper. So I'll end by briefly asking, how tight is our new vector tail bound? This bound is parameterized by at least the 3 parameters gamma, the effective dimension, and this ratio between our radius bound and the radius of the spherical shell. So these 3 different parameters convey that there's potentially a lot of structure here. So to simplify this expression a little bit, this ratio essentially falls into 2 regimes depending upon which term in the denominator is bigger. So up to constant factors in the exponent, we can simplify this as just gamma squared times the min of these 2 things. So this is an upper bound. To understand how tight it is, we need to understand lower bounds. This upper bound applies for all distributions. The lower bound is going to come from a single distribution. Each lower bound is going to come from a single distribution whose tail we can analyze. One distribution worth looking at is the Gaussian. And as we've pointed out, the gamma squared times effective dimension portion of this upper bound essentially represents the spherical shell behavior of the Gaussian. So for this one regime, where the effective dimension term dominates here, the performance of our upper bound, in fact, matches that of the Gaussian. A different lower bound regime worth considering is a much spikier, less uniform distribution, where the distribution is supported only on the axes and as far out on the axes as our radius r bound will allow. There's in fact two subregimes of this that have rather different behavior. One is when the tail is likely to be along a single axis. The other is when the most extreme tail events are likely to come in intermediate directions with contributions from support points at many different axes. So our upper bound has these two different regimes, depending on which term dominates, and we have three different regimes for lower bound. I'm going to draw a picture, a diagram that tries to convey what's going on here. So I'll depict the three-dimensional parameter space by projecting to a triangle where points near one vertex of the triangle correspond to one of these three different parameters being higher than the other two. So the two different parameter regimes of the upper bound are when the effective dimension is bigger or smaller than this root trace term, which corresponds to being in the left or the right side of the triangle, represented by this cross-hatched black pattern here. Meanwhile, the three different lower bounds, the regions in which each of them dominate the other lower bounds are depicted by these three colored regions that match the three lower bounds. And okay, so conveniently, the crosshatched region and the black region have the same bound here, indicating that for the entire right half of the triangle, our upper bound is in fact tight. On the left half, though, the situation is much more complicated. We have three different lower bounds that each dominate in different regions of the triangle, and none of these three expressions match the corresponding upper bound here, gamma squared times this root trace thing. So our upper bound is tight for half the parameter space, and for half the parameter space, things seem rather complicated. So I think it's worth looking at this structure, and because it's such a high dimensional parameter space, this diagram hints that there's actually a lot of further structure worth understanding with these new vector tail bounds. Contributions. Our main result today is a simple linear time 1 plus log of 1 factor optimal mean estimation algorithm that works in very high dimensions. The tool we use to get this is a new vector Bernstein inequality capturing the intuition that high dimensional Gaussians behave essentially like spherical shells, and extending this intuition to the tails of arbitrary banded distributions. Two new contributions which I haven't mentioned. One is a new tight 1 plus log of 1 factor lower bound for mean estimation from an algorithmic perspective. So in the high dimensional regime, this 1 plus log of 1 accurate analysis hasn't really been discussed before. And these lower bounds, in principle, would be useful for future work along this line. Finally, the coordinate-wise median of means algorithm we use as a subroutine, and we have a new tighter analysis of this, which removes a spurious dependence on the ambient dimension D. Okay, thanks.